generate some data, right? So that's what you have seen in the yesterday's demo sessions and the lecture sessions. So today what we will do is we will try to see what are the different metrics, right, on which these models can be evaluated. So by evaluation, I mean, suppose there are 5 different models and all these models are trying to solve a specific task, then how these models are performing on those tasks, right? So some models might be doing very good, some models might be not doing that good, right? So this is the kind of comparison we want to do, and for that there are some very popular standard metrics which we will be looking to today. Okay, but before that, let me just read out a brief recap of what we have done. So we have looked into NLP tasks, right? We have looked into NLU, we have looked into NLG, natural language understanding and natural language generation, and different tasks which come under these 2 subtypes, right? We have looked into the traditional NLP pipeline, which has 4 stages, right? We have also looked into the modern NLP pipeline, which also has a 4 stages, but a very different kind of way to solve the same problems, right? Then we have looked into how we can clean the data, how we can pre-process the data, right? And then during the lab session, we were talking mostly about how we can kind of implement a modern NLP pipeline, right? So implementation wise, again, I accept that you might not have that much fluency in understanding, but again, this is just based on your practice. The more you will practice, the more you will learn. Okay, but our task was just to showcase that yes, indeed this can be done, and this can be done very easily. So within one day you can implement this entire NLP pipeline in your systems, right? That was our kind of motivation. Okay, so let us look at some popular evaluation metrics. I hope you remember we have talked about some text classification tasks, right? And one of the very popular text classification tasks is sentiment analysis, right? So in case of sentiment analysis, you are going to get these kind of reviews, and for each review you will assign some class, right? So assume that these reviews that you are seeing here, we have taken them from Amazon, right? Amazon website, and these are not from Amazon India, they are from Amazon United States. And so these are just 10 reviews which I have randomly picked from the Amazon website, right? And for each review that you are seeing here, we have also assigned a class, whether that review is a positive review or a negative review, right? To a human, remember this one, to a human, what is this review sentiment, right? So that's what this actual class represents. So actual means the real class to a human, right? And the motivation is that we want to create a classifier which predicts the sentiment similar to the actual class. That's the kind of simple, very simple idea, right? So here this 1 represents a good product or a good service, right? And 0 represents bad product or a bad service. It's very simple, right? And that you can read out these reviews also, and you can see that yes, indeed it is the case. Okay, now assume that we have trained some sentiment classifier, right? We have seen a lot of sentiment classifiers yesterday. So suppose we have trained some sentiment classifier and we have passed each of this sentence through that, right? So we are just passing one sentence at a time through that sentiment classifier, and it is predicting its class, whether that is a positive or a negative. Okay, and the 4th column here, the predicted class, is actually the predictions coming from your sentiment classifier, right? So if you see here, for the first example, its actual class was 1 and the predicted class is also 1, right? This is how we are going to read it, right? For the second example, the actual class is 0, right? That means it is a bad product, and the predicted class is 1. Then for the third one, the actual class is 1, the predicted class is 0, right? And so forth for each of the 10 examples, right? So I think in one of the initial lectures you have been taught about false negatives, true positives, and so on and so forth. Okay, so what do you think about this? Is what type of class is this prediction belongs to? True positive.
True,
Okay.
true positive. Yeah.
So this is true positive. Very good. What about the second one?
This is false positive.
This is false positive. The third one?
False negative.
This is false negative. The fourth one?
True negative.
True negative, right? And so on and so forth. Yes, that's what this fourth slides gives me. Again, you know, right? It's not that difficult. Okay, so what can we do now? Were you told about computing metrics like precision, recall, accuracy, F scores? Okay, so what will be the precision here? Given these values, what will be the precision? So what is the formula of the precision? Precision is equal to
True
yes.
positive by true positive plus false positive. Yeah.
Okay, so it is true positive divided by sum of true positive plus false positive, right? Is that correct? So what would be that value here for our example? What would be that value for this example, the precision? At least I know this thing, right? So precision is true positive divided by true positive plus false positive. What is that value going to be in this case? How many true positives are there? 2. Okay. And how many false positives are there? 3. Right. So this is going to be how many? 2 by 5. Right. So this value is going to be 2 by 5. What about recall? So this example is a very simple example, right? I will tell you what is a difficult example. So just for practice, let us calculate the recall also. So what is the formula for the recall? Okay, so you are saying true positive in the numerator and in the denominator true positive plus false negative. What would be that value? What is going to be that value here? 2 by 5. What is going to be the value of the accuracy? Let's not talk about F score. What is going to be the value of the accuracy? So I hope this has been taught, right? That's why I'm just asking you the questions. Otherwise, I would have given you the formula and then calculated also. So what is going to be the value of the accuracy? So like again the formula first. Total number of correct predictions upon total number of examples. So how do we define the total number of correct predictions? True positive plus true negative, right? All these are correct predictions divided by total number of predictions or total number of examples, right? So that include true positive plus true negative plus false positive plus false negatives, right? That means the entire all the instances. What is going to be this value?
I think it's 3 by 10.
3 by 10.
Sorry.
Okay, so someone is saying 3 by 10. What do you think? Is it going to be 3 by 10 or something else?
5 by 10.
5 by 10?
Sorry. Yeah.
So at least the denominator, I'm clear, it is going to be 10, right? So denominator is 10. What about the numerator? How many true positives are there?
2 by 10, sir. There are 2 true positive, 0 true negative.
And two true negatives also, right? So it is again going to be 2 by 5, right? And then you can also compute recall, which is just the harmonic mean of F score, which is just a harmonic mean of precision and recall, right? I hope that is also taught to you. Okay, so if you just see this slide, this is how the things have been computed. Right. This looks like a very nice example. Okay, so this looks like a very nice example where there are no difficulties. But in real scenario, this is not what is going to happen. Right. In the real scenarios, the data sets are very biased. Right. So very biased means there is a huge class imbalance. So that means majority of the training instances might belong to just one class, whereas a small proportion of class belong to the other class. A small number of instances belong to the other class. Right. For example, we are talking about detecting Facebook posts which are hateful. Detecting Facebook posts which are hateful. Right. So if you see the non-hateful tweets or the non-hateful posts, they are very large in number. But the hateful posts are very small in number. Okay. So that can create problems. How will it create a problem? So the question is the following, that this was a very nice example, right? The classes are balanced, equal number of positives, equal number of negatives, right? But in real data, you are not going to find the same thing, right? As an example, you can create a detector which detects Facebook, the hateful Facebook posts, right? In that case, almost 95% of the posts will be non-hateful, and 5% posts are going to be hateful, right? Will the same metrics work there? Why? Can you come up with an example? Okay, so you are saying it will predict non-hateful as hateful or hateful as... Okay, so let us not worry about the model, how it is predicting. Let us worry about the evaluations, right? So right now we are just talking about the evaluations. Assume that our model is very good. Whatever it sees, it predicts correctly in most of the scenarios, right? But these metrics, will they capture the performance of the model correctly or not? That's the question. They will not be able to do it, right? Let us try to understand this with an example. Suppose I'm creating a small confusion metric, right? So here we have the true values and here we have the predicted values, or I would say the actual values, and here we have the predicted values, right? You are aware about what does this confusion metric represents, right? Okay, very good. So you have some hateful messages, you have some non-hateful messages, right? Same, we can also write it here, hateful and non-hateful. In general, suppose you have 100 instances, right? And 95% of them are non-hateful, right? So actual case may you have hateful as 5% and non-hateful is 95%. Okay, and suppose you have 100 instances, so 95 are non-hateful, 5 are hateful. Okay, let us consider a model, some dummy model, which assigns these classes according to this confusion metric. Okay, so let us try to fill this confusion metric. Assume that we are talking about the hateful messages, right? So in total, how many hateful messages are there? 5, right? So let us say that maybe 2 hateful messages were predicted as hateful, whereas the 3 were predicted as non-hateful. And similarly, for non-hateful messages, maybe we can say that, or maybe just one of the non-hateful message was predicted as hateful, right? And the rest 94 non-hateful were predicted as non-hateful. We can always have a model like this, which can predict the way we have kind of created this confusion metric, Right? We can always create a model like this, right? That's not a difficult thing. So what is going to be the precision of this model? What is going to be the precision of this model? That's the first question. And how will you define the precision? I just know one thing, that the formula of the precision is what? True positive divided by sum of true positive plus false positive. That's the formula I know, right? But we have to define it. What class I am going to consider as positive? Right? Otherwise, we cannot define what is the precision here, right? So what class do you think can be considered as a positive? Hateful or non-hateful? What do we want to predict actually? Hateful, right? So in that case, things or the instances which are predicted as hateful or which were hateful actually will be considered as positive. Rest everything will be considered as negative, right? So how many true positives are there?
We have two.
Huh?
Two.
Okay. And false positives? False positives? 3? Three or 1? False positive. 3 or 1?
3, sir.
3? How many of you want to vote for 1?
3, sir. 3.
3. Okay. So someone from the online audience is saying 3. How many of you vote for 3? How many of you are voting for 1? False positive. The predicted class is positive, but it is incorrect prediction. That's what this false positive says, right? So what is that value going to be? 1 or 3? 1. Right? So false positive is 1. Right? So what is going to be your precision? Two by 3? Okay, very good. That seems to be very good. That seems to be very good, right? Again, here there are 2 caveats. The first caveat is you have to define what is your positive class. Right? What if I had defined non-hateful as my positive class? Then this precision value would have been changed, right? You would have to again find out what are the number of true positives and what are the number of false positives, right? And then you would have kind of computed this precision values, right? So in general, it is sometimes very easy to identify what is my positive class, right? But that might not be true always. For example, you have a very simple classifier, right? And which classifies this thing, that it takes the news article as an input and it assigns a topic to it. Topics could be film, topics could be related to politics, related to environment, related to Bollywood, and so on and so forth, something like that. Okay, so this time you have multiple classes, right? I cannot say that this class is positive, the rest are negative, or the class film is a positive, the rest of them are negative, right? So what we have to do in those scenarios is the following, that for each class we have to compute or calculate this precision, and then we have to average this out. And this is what it's called, average precision of the classifier, right? So these are like ways to, again there can be caveats here. So if you are just averaging over all the classes, the precisions of all the classes, it is kind of a very simple average, right? But not all classes are equally balanced. Not all classes are in equal proportion in our data set, right? Then you can have a weighted average precisions also, right? So that depends on what kind of data you have, and accordingly you have to define your metrics, right? That's why I told you in the beginning, like in the yesterday's second lecture, that it is always important to look into your data first and then to try to create a model for that and then to evaluate it, right? You should be very clear with your data. How is your data looking? How the labels are distributed and so on and so forth. Whether the metric on which you are going to compare your models is a good metric or not, right? So this is all is kind of important. Okay. Okay, so that's good. That's good. At least you are aware about this precision, recall, accuracy, F scores and everything from beginning, right? And then we just talked about a very simple case, right? Now let us talk about something which is very much NLP oriented, right? So let us talk about a summarization task. Idea is very simple, that you have a source document and you want to create a summary. Right? You have a document, so you have a black box system, a model. You are passing a source document, and this system generates a summary. Right. So in general cases, usually this source document is going to be very large like the Wikipedia pages of different personalities, right? And this summary is going to be very small summary, a small paragraph, maybe that contains 5-6 sentences, not more than that. Okay. So this is kind of a systems we want to evaluate. Which system is generating the best kind of summaries, right? Okay, so I hope the task is clear, right? So there can be two different types of evaluations. In NLP, you can always do two types of evaluations. The first type is called extrinsic type of evaluations. The second type is called intrinsic types of evaluations, right? So extrinsic is very simple. You are generating these summaries, right? So given a source document, you are generating all these summaries, right? Instead of directly evaluating it, you pass these summaries to some other task, some other NLP task, right? And then you evaluate the performance of that task. If your summaries are good, that means the performance of that task will also be good. That's the kind of an assumption. Okay, so that is called an extrinsic. So you don't have a direct way to measure the quality of your summaries, but there is third task whose performance indirectly will measure the performance of this summarization task. Again, not very popular. This is not something that is very popular. Right? What is more popular are these intrinsic measures. Right? So what you have is, let me just, instead of just reading it, let me tell you the intuition. In case of intrinsic summaries, suppose this is the summary which has been generated by machine. Right? So we'll call it as a machine generated summary. We also have summaries which are generated by humans. Right? So to this human, you have given the same source document, right? And the human is generating a summary, right? So what are you going to evaluate? How are you going to evaluate the machine generated summary? You will compare it with the human generated summary, right? And if those summaries, the two summaries are very closer to each other, then that means the model is performing well. Very simple idea, right? So this is called intrinsic summarization, intrinsic evaluation of the summarization task, right? So extrinsic is a different thing, intrinsic is a different thing. Intrinsic is more popular. Now, what is the challenge here in this evaluation? Pardon? No, it can be, again, it can be extractive based summaries also, that is possible. So I'm not talking about that aspect, but it can be. Human has just picked the best sentences from a paragraph. So extractive summaries are also possible. So one of the challenges to create this data, to create human summaries, right? We need humans to create these human summaries, right? And that is a difficulty, right? That is the reason you don't find a lot of generation tasks, right? Summarization is one of the generation tasks, right? So you don't find a lot of generation tasks because even if you can create a very good model, you don't have data sets to evaluate your model, right? That is a big problem. Okay, that is one problem. What is the other problem you can think about? Okay. Okay. Yes, but that is a problem with the generation. I'm talking about the problem with the evaluation, where humans are there for the evaluations. Maybe we'll look into some metrics. We'll look into some metrics and their challenges. Yes, human bias, right? The way I am generating a summary might be very different the way you are generating the summary for the same document. Multiple humans. So one possibility is we take multiple humans to generate the summary for the same document, right? And then for the machine generated summary, I compare it with the summaries generated by different humans. That is also possible, right? So this is actually what is done in the real scenarios, right? So you have a machine generated summary, you are comparing it against multiple human generated summaries, right? Now, if the machine generated summary is very similar to this human generated summary, we can consider it as this is a good quality summary generated by the machine. Okay, so this is the intuition at least, right? Let us see the formula. So in order to just implement the formula, the things that we have talked about, we kind of use a metric called ROOJ. Right, again, very complex name, recall oriented understudy for gisting evaluation, gisting in summarization, right? And recall, I will tell you later why it is called recall, but idea is that it just follows the intuition. If my summary is very similar to the reference summaries, the reference summary, I mean the summaries generated by humans, then that means my summary is a good summary. That's all. Okay, so what it does is the following. I'm talking about this ROOJ2. ROOJ can have different forms. So ROOJ is just a metric. I can call it as ROOJ1, ROOJ2, ROOJ3. I will tell you what this 1, 2, 3 represents. And then there are other forms of ROOJ also. Okay. What it says is the following. So let us first of all define bigrams. Are you aware about bigrams? So not many people are aware about the bigram. So bigrams can be constructed like this. Given a sentence like this, what are the bigrams? You take two consecutive words together. Right? For example, given A, this is a one bigram. A document, this is another bigram, right? Document D, this is the third bigram, right? D and this is the fourth bigram. And N, this is the fifth bigram, and so on and so forth, right? So just two consecutive words. Two consecutive words will constitute a single bigram. Okay, so what does this 2 represents? That we are going to measure the similarity of we are going to measure the overlap of bigrams between the machine generated summary and the human generated summary. How many bigrams are common between these two? That's what we are going to compare. Right? If it is ROOJ2, if it is just ROOJ1, then we can simply say we are just going to compare the overlap of tokens or unigrams. If it is ROOJ3, then what does it mean? We are going to compare the overlap of trigrams. 3 consecutive words. How many such 3 consecutive words are common between the human summary and the machine generated summary? Is that thing clear? At least, right? What does this 1, 2, 3 represents in the ROOJ? Right. Now let us see the formula. Let me just rewrite it in a very simple term. This looks very complex. In the denominator, it is total number of bigrams in reference summary. In the denominator, it just has the total number of bigrams in the reference summary. Reference summary means the human generated summary. In the numerator, it is the number of common bigrams between the reference summary and the machine generated summary. That's all. In the numerator, number of common bigrams between machine summary and human summary. Right, the same intuition. The intuition remains same, just the formulation, and the formula looks very complex, right? But this is the idea. Okay, so let us see this with an example. So this automatic summary means summary generated from the machine. Reference summary means summary generated by the human. What do you think will be the ROOJ2 score? How many bigrams are there in the reference summary? So in the denominator, what is going to come? The number of bigrams in the reference summary. Right? How many bigrams are there in the reference summary? 6. This is 1, 2, 3, 4, 5, right? So this is 1, 2, 3, 4, 5. So at least in the denominator, we are going to have 5. In the numerator, the number of common bigrams between the reference summary and the machine generated summary. How many? What will be that value?
4. We have 4.
7 or 4? No, 7. It cannot be 7.
4.
Not
4
more
sir.
than 5.
We have 4 only.
It will be 4.
Yeah, the cat was found under the bed.
Number of common bigrams. So let us see. Right. One bigram is the cat. The other bigram is was. And found under
the bed.
So how many common bigrams are there? 4, right? It is going to be 4 by 5, right? So this is kind of a very good model, which has generated this summary, right? Almost 4 out of 5 bigrams are matching, right? So this value is never going to be more than 1, because the reference, you cannot have more number of bigrams than the reference. You should have maximum 5, minimum could be 0. None of these bigrams are matching. Is this thing clear? Right. Yes. Yes. So again, I will tell you. I will give you some more intuitions, and then maybe I can answer this question. Right. Okay. At least this thing is clear. Right. We'll look into one more metric, which is exactly similar to this one. And yeah, so this is that number. And these are called Rouge L, Rouge S, and Rouge SU. Right. Again, different variants of the same Rouge, right? So Rouge 1 is like, we are just, instead of taking bigrams, we are taking unigrams. You can also have Rouge 3, which is trigrams, right? So Rouge L is, Rouge SL measures the longest subsequence. The longest subsequence between the reference summary and the machine generated summary, right? A model is good if the length of this longest subsequence is very large. Right? That's what it measures. Rouge S is a skipgram based similarity. So skipgram means 2 consecutive words might not be matching, but 2 words that have the same order, even if they are far apart, are overlapping between the 2 summaries. Right? For example, for given this reference summary, maybe we have this kind of summary. Right. So you have tokens like bigrams like the cat was under the bed, right? All these bigrams are there in the reference summary. In my automatic summary, I have skipgrams. If we're talking about skipgrams, right? Then we have this skipgram, this the was. We also have a skipgram, the cat. Right. So if in case of skipgram, the idea is very simple. We can skip some numbers, but the ordering should be same. If we can find those bigrams also, overlap of those bigrams also, then also we'll consider that as a good case. Right? That's the simple idea behind a skipgram, right? So not necessarily the consecutive occurring bigrams, right? So bigrams, we'll consider those bigrams also, which are following the same order, but they might not necessarily are in the consecutive order. Okay, that is called Rouge S, right? And then Rouge SU is an extension of Rouge 1 plus Rouge S. Whether you have skipgrams matching or unigrams matching, both of them will be considered as matched, right? And that is called Rouge SU. Okay. Now, again, there is no as such paper which says whether you have to use just Rouge 2 or Rouge 3 or Rouge 4 or Rouge 1. Right. Again, it is just standard of what Rouge values or what type of Rouge metric is becoming popular in the community. So usually it is Rouge 2, Rouge L, which is popular in the community. Right. Again, there are no merits or demerits as of, right? But it's just the popularity of what people are using these days. Right. Okay. Okay, so let us talk about another task. This is what? This belongs to NLU or NLG? NLG or NLU? NLG, right? We are generating text. We are generating text. We are kind of creating these translations. So exactly same idea. For a source text, we are generating translations, right? So we are, for the source text, we are generating translations, right? So we have a model. You are passing, suppose, a sentence. I'm calling that as a source sentence, right? And then it generates its target translation. Again, this looks very similar to a summarization task, right? If we have human generated translations, we can always compare our machine generated translation with the human generated translations, right? So we can always use Rouge here, right? But this new metric was proposed for, at least for this task. I will tell you also the difference between these two, right? So you can always use Rouge to evaluate machine translation task, right? But what is this blue? So blue was, okay, again, this is not correct. So blue was mostly used for this translation task, right? And the idea is very simple. This time, in the denominator, you are going to have, suppose I'm talking about blue 2, right? So this is going to be the number of bigrams in machine generated summary. Machine generated summary in the denominator, and in the numerator you have the number of common bigrams between the machine generated, not the machine generated summary, I would say translations, right? We're talking about translations. The number of common bigrams between the machine translated translation and the human translation. So what is the difference here? What is the difference here? The difference is just in the denominator, right? Rest is almost the same idea. Okay. So the Rouge metric, we used to call it as a recall based metric. And this blue, we used to call it as a precision based metric. Why so? Can you give me the answer? I will anyway tell you if you cannot give the answer. Why are you calling blue as a precision based metric, and why you are calling recall as a, or the Rouge as a recall based metric? You can get a idea from our initial discussions, right, where we have defined precision and recall. So what is this precision measures? Right. It's just computing this proportion, right? The number of correct bigrams among all possible generated bigrams, right? So that is actually the basic intuition behind precision also, right? If we just talk about precision, right, the kind of precision we have done it for text classification. What was that measuring? What is the total number of positives, correct positives among all predicted positives? What is the proportion of the correct positives among all the predicted positives? Same thing is here also. What is the proportion of the correct bigrams among all the predicted bigrams or all the translated bigrams, generated bigrams, right? So this blue is a precision based metric, and recall is what you are comparing against the reference summary. Same is the actual difference of the recall also, right? The definition of the recall also. That time what we used to say, among all possible correct predictions, how many of them are actually predicted? That is how we define recall, right? Same thing is here. Reference summaries are what? Those are the correct ones. Reference summary bigrams are the correct one. How many of them are the correctly or are actually present in my generated summaries, right? So I hope the distinction between these two is clear. Recall based and the precision based. Okay. So for machine translation tasks also, instead of computing blue, you can also compute rouge. Right? Both way it is possible, right? But you should be clear with the differences. Why precision based, why recall based? Okay. Now it depends that, so whether for a given task precision is useful or recall is useful, it depends on that task. Right. For example, you want to create a classifier, right, which looks into the medical history of a patient and it predicts whether that patient is possibly a cancer patient or not, or whether he will get a cancer in near future or not. Right? What do you think? Should it have a high recall or should it have a high precision? Precision or recall? What is more important for this kind of classifier? Precision or recall? Recall. It is fine if he doesn't catch cancer, right? But the recall should be very high. That means if he is a likely candidate, then he should be predicted that he will catch cancer, right? So in this case, precision is not that important. Even if your model has a low precision, that is fine, right? But the recall should be very high. Can you come up with a task which requires high precision? Recall is fine. If recall is poor, it's fine. Rain prediction. Okay. Yes. Right. So rain prediction, again, I'm just talking about some NLP. Can you come up with some NLP task which requires high precision? Think about it. Think about it. There are a lot of NLP tasks which require very high precision, even if we do not want very high recall. So that's fine. Recall. No, I'm just talking about something related to NLP. There are a lot of other domain problems where we need high precision. Yes. Directions by voice matching. Yes, that could be one possibility. Right. So we want very precise answers there. Right. Yes. Thread prediction in social media posts. Okay. So what do we want there? We want to predict whether a post is a threat to someone or not, right? So we want it to be very precise, right? Yes, that could be, one of the examples. Right. What about hateful hate message detection? Recall or precision? Precision or recall? Is it fine to kind of ignore some of the hateful messages, or if not, then recall is important, right? And what if we are predicting most of them with very poor precision, then what will happen? So what will happen if suppose we are predicting almost everything as a hateful, then? Right. So it again depends on the kind of resources you have, right? Suppose there is just one person who has to look into the messages which are predicted as hateful, then it can become a problem if your model has a low precision. Right? Because everything will come as a hateful, and then that person has to decide whether this is actually hateful or not, right? Whereas if you have a huge team, then you can have a model which has a high precision, right? Then the people will kind of filter it out later. Again, this depends on your resources also. Okay, so this is what it tells us, that blue versus rouge. Okay, let us just talk about one more metric. Again, this is very important metric for generation tasks, right? Generation tasks like summarization, generation tasks like machine translation. Okay, so whatever metrics we have seen till now for generation tasks, again, they are very good, right? But this time we are talking about an intrinsic metric, and this is called perplexity. So perplexity of a generated sentence this W is some sentence. Sentence is what? Sentence can be defined as a sequence of words, right? So W is some sentence. I want to compute the perplexity of W. And the way I have defined it as the probability of that entire sentence, the inverse of probability of that sentence. So W is what? W is some sentence, and it is composed of words like W1, W2 till Wn. Right. And the perplexity of that sentence is inverse of the probability of that sentence. Let me just define it like this. Okay. So if the sentence is highly probable, its perplexity is going to be very low. Right. You can think it in this term. I will tell you how to compute it. Right. If the probability of a sentence is very low, then the perplexity is going to be very high. Okay, at least this is clear. We'll tell you whether good perplexity is good or bad perplexity, high perplexity is good or bad perplexity. Okay. So, but before that, let us see how we can compute the probability of a sentence. Right, we have to compute the probability of a sentence to compute perplexity. Right, so let us see. So consider a sentence W. Consider a sentence W which has these tokens W1, W2, W3 till Wn. Okay. And we want to compute the probability of this sentence W. Right. So that means what? We want to compute the probability of this sequence of words. Right. Can we write this sequence of, can we write the probability of this sequence of word like this? What is this? What probability theory? Is this a chain rule? Is this
Conditional.
chain rule of probability? Can you write it like this?
Yes, sir.
Right. So it is again. So the occurrence of word is like occurrence of some events. Right. Now occurrence, the joint probability of occurrence of these events can be modeled like this. Right. The way I have modeled the joint occurrence of these words. Right. You can write it like this. Probability of W1, then probability of W2 given W1, probability of W3 given W2, W1, and so on and so forth. What is this rule? Chain rule. Right. So what does it say? It says the probability of a sentence can be computed like this. The probability of a sentence can be computed like this. Right. I have not yet told you how to compute these small probabilities, right? But this is a very simple formulation that we can use. Okay. Let us move ahead. Let us take one assumption. We are calling it as a Bigram assumption. Okay. Again, you have done this Markov models yesterday. So in case of Markov models, we can define that how many past events we have to see to predict the next future event, right? In case of Bigram assumption, we can the current event only depends on the previous event. That's my assumption, right? So if that is the assumption, we can simply write this probability as this. Can we write it like this? Again, this is assumption.
Yeah. Yes, sir.
Right? So
yes.
Here we are saying that W3 conditioned on W2, W1, right? Here we are saying Wn conditioned on Wn minus 1, Wn minus 2 till W1, right? Now occurrence of Wn doesn't depend on Wn minus 2, Wn minus 3, and so on and so forth till Wn, right? It only depends on Wn minus 1, right? So simply we can write it like this. Right. So the probability of a sentence, you can write it like this. At least this is simpler than what we have seen in the previous slide, isn't it?
Yes, sir.
Right. Okay. Now the challenge is, how are we going to compute these values? At the end, we have to compute these values to compute the compute the perplexity values, right? So we have to compute these probability values from the real data. So that is the challenge, right? This is all on the real data. Nothing is hypothetical. So everything is on the real data. How can we compute the probability of a word W3 given W2? How can we compute the probability of W2 given W1? Right? And so on and so forth. So let us see. This is how you are going to compute the probabilities, this bigram probability. So what does it say? Probability of wi given wi minus 1. This is equal to count of how many times this bigram has appeared in my data. Count of this bigram in my data. So what is my data? So maybe you can download this entire Wikipedia data. Find out how many times this bigram was occurring in that data. I'm talking about that count in that numerator. How many times this bigram is there in your Wikipedia data, divided by the count of this unigram. How many times this word is present in your Wikipedia data? This is the probability. This is this bigram probability. Probability of wi given wi minus 1. So what does this say? What is this? This proportion is talking about. Every time, whenever wi minus 1, a word wi minus 1 is occurring in my data, how many times it is succeeded by a word called wi? For example, I'm talking about this word. So assume that wi minus 1 is the and wi is cat. Right. So what would be in the denominator? Count of the. In the numerator, right? So that's what it says. In your huge corpus from where you are computing these probabilities, how many times the word da is present, that will come in your denominator. And out of that, how many times da is succeeded by a word cat. Right? This is going to be the probability, this conditional probability of cat given da. Is that correct? This is how you are going to compute these probabilities. Right. So if you can compute this, you can just put these values here. And you can just calculate the probability of a sentence. Now you can always ask me how will I compute this probability of a given word? That is again very easy. Probability of word wi is equal to count of wi divided by total number of tokens in the data. Right? So if you have all these values, you can always compute the probability of a sentence, right? If you can compute the probability of a sentence, you can compute, just take its inverse, it will be the perplexity. Is that correct? Any doubts? Any doubts? Remember the assumption. The assumption is that we are following bigram assumption. Right? The word is only dependent on its previous word. Right? We can also take a trigram assumption that the word is dependent on its two previous words. And quadgram assumption, right? That is always possible. Any doubts here in computing these values, right? That's not difficult, right? So we can just compute these conditional probabilities. We put their values here. We can get the probability of the entire sentence, right? If you can get the probability of the entire sentence, you can just compute the probability of the perplexity of that entire sentence. Right? Okay. So what does it say? If your sentence is highly probable, the perplexity is going to be very low. So if your model is very good, if your model is generating very good quality sentences, then the probability of the sentences that it is generating is going to be very high, right? And that means the perplexity is going to be very low for that model, right? So we should aim for models whose perplexity is very low. That's kind of a very simple intuition behind using this perplexity, right? Now, one more thing here, which is very important, is perplexity is a domain independent evaluation metric. Right? You can compute perplexity for translation tasks also. You can compute it for summarization tasks also, right? So it is not dependent on the task that you're trying to solve, right? What it tries to measure is how good is your generated text, how good it is in comparison with the human generated text, right? Does it follows the same kind of grammatical structure of your human as the humans have generated this text? That's all, right? Whether this text is going to be as good as very good summary, or whether that text is actually a very good translation, it doesn't talks about that. For those, you have this blue and the rouge metrics, right? Those are task specific metrics. Is that thing clear? Right. So whenever you come up with, or you are trying to come up with new generative models, you should try to test your model on both of these types of metrics. One is a generic metric, this intrinsic metric perplexity, and one is this task specific metrics. Right. Okay. Any doubts here? Yes. Yes. That is highly likely, right? And in that case, so this kind of the perplexity definition that you are seeing here, this is defined the way we used to work in the old traditional NLP pipe, right? For the new tradition, for the new kind of NLP, again you can compute perplexity by using cross entropy, right? So if you have any kind of deep learning model, right, you are going to generate the embeddings, the vector corresponding to that sentence, right? You can compute the cross entropy, right, from that, and using that cross entropy, you can compute these perplexities, right? So there is a nice relation between this this cross entropy and the perplexity there also, that you can use that to. So there we are not kind of computing these probabilities, P of W1 given W2 or W2 given W3 and all this, right? We compute cross entropies. From cross entropy, we derive this perplexity values, but it can be done. And those embeddings takes care of all these synonyms and antonyms and all this, right? So if two sentences are closer to each other, even though they might not contain any same word, but they are synonyms, then also their vectors are going to be very similar to each other, right? So that's again, I've not told you, but yes, it can be done, right? Okay, so just one thing before I move ahead. Let's talk about this blue. Let's suppose talk about this blue metric, right? How can we kind of cheat this blue metric? Is there a way to kind of, even though my model is not good, but can we do something so that we can produce better blue scores, right? In the numerator, you have the number of bigrams in the machine generated summary, right? If we can come up with a model, or I just kind of create a model, even though the translations are not good, but the length of those translations are very small, right? In that case, you are going to achieve very high blue scores, right? There is a way around to how to tackle this, but yes, people have kind of showed that yes, indeed, these kind of things can create problems in the evaluations, right? Okay. So what does this entire story tells us? There are so many metrics, and we are just interested in their numbers actually, right? Blue score is what? It will give you some number, right? Perplexity will give you some numbers, right? With a low score of 10 or 12 might say that this model is very good, right? Same is true with precision, recall, accuracy, and all, and so on and so forth, right? So sometimes, even if these models, and I've showed you those benchmarks, right? All of these benchmarks were giving you around 95, 96, 97, 98 kind of performance scores, right? So that means all these tasks are already solved, nothing is left in NLP. But when we put these models in the real scenarios, they perform very poor, right? How they perform very poor, we are going to see this, right? And how we can measure this performance, not just based on these numbers, but maybe based on some other form of testing, right? That's what we are going to see this. Okay, so there is this topic called behavioral testing of NLP models. I want to test the models which have been proposed for solving some of the NLP tasks, right? By just not looking into the numbers. I just want to test their behavior for different types of inputs, right? And I want to test their capabilities, right? So I will define some capabilities. I will check those capabilities, right? If the model shows very high scores for those capabilities, I can always say that that model is good. Okay, so this was one of the best paper in a very popular natural language processing conference in 2020, and this is called the Beyond Accuracy Behavioral Testing of NLP Models with Checklist. Right, I will define what I mean by checklist and how we can create this checklist. Okay, so idea is simple. Let us try to read this table. I'm not explaining you the entire paper. Let us just read this paper or read this table. So they have experimented on multiple tasks, right? Since we have covered extensively sentiment analysis, so let me just start with the sentiment analysis task. So idea is there is a model, some black box NLP model again, right? You are passing a review to it and it predicts its sentiment. Positive, negative, neutral, positive, negative, neutral, right? Okay. They have experimented with several NLP models, right? What are those models? They have experimented with 3 industry specific models. So these models, for these models, these authors have paid money to the different companies, because these models you can only use if you can pay money to the companies, right? So these are very well maintained by the companies, and people and the organizations pay to use these models, right? They are not free and they are under production, so people use it for their productive kind of for their products. So one is from Microsoft, one is from Google, and one is from Amazon. Real world production based sentiment analysis tools, very powerful sentiment analysis tools, right? Then they have also experimented with 2 academic tools. Academic tools means they are openly available, their source code is available, you can implement them, right? You can experiment the way you want. So those are they call it as, they have experimented with the model called BERT. They have also experimented with the model called Robert. Just remember that all these are deep learning based models. None of them are traditional NLP based models, right? And all of them perform the same task, sentiment analysis. Given a review text, they will predict whether this is positive, negative, or neutral. Okay. I hope the problem or the experiment settings are clear to you. Okay. Now what they are saying is that instead of just computing the accuracy of these models, we will first of all identify some capabilities that ideally, in ideal scenarios, a model should have some linguistic capabilities, right? So one of the linguistic capability of any NLP model should be that it should have a good vocabulary. It should have a very good vocabulary. By having a very good vocabulary means it should be able to understand the words that are going to come as an input to that model, right? If a model doesn't have a very good vocabulary, it will not be able to process the words, right? So to test this capability, whether a model has good vocabulary or not, they generated some sentences, right? Some review sentences. Okay, so what they are saying is this: they are trying to generate sentences which they will pass to these models, and they generated 3 different types of sentences, right? One they call it as MFT, one class they call it as INV, and one class they call it as DI. Right. So MFTs are those sentences which are very small in length. Just consider them as like very small in length, and they have a specific sentiment associated with that, right? Like I like iPhone 12. So that is a positive, that has a positive sentence. Very simple sentence which has some associated sentiment to it. Okay. This is what they have defined as MFT. Then they have also defined INV. So maybe INV means given a review sentence, right, they will replace a neutral sentence with some other neutral sentence, right? So if your model was predicting the earlier sentence as neutral, after this replacement, it should again predict it as a neutral only, because we have just replaced the neutral with a neutral. It should not start predicting as a positive or a negative, right? So this type of sentences, they call it as like invariant based examples, right? And the third kind of sentences that they have generated are called directional. So that means, given a positive review, I will add some more positive words to it. But if my model starts predicting it as a neutral or negative, that means the model is not. Right. Same thing true with the negative case also. Suppose I have a negative example. I started adding some negative words to it. It will become more negative. Right. But if my model starts predicting it as a positive or neutral, that means the model is not good. Right. This is very simple experiment to check whether my model has a good vocabulary or not. Right. Okay. So what they are showing here is these different classes of sentences that they have generated. Okay. So MFT, in case of MFT, they have generated two types of MFT sentences: short sentences with neutral adjective and nouns. Some very short sentences with neutral adjective and noun, right? For example, the company is Australian. That is a private aircraft. These are short sentence with neutral adjective or nouns, right? And what is our expectation from the model? It should predict it as neutral. Fine. It should predict it as a neutral. The numbers here show the failure rate for these kind of for this very simple experiment. If you see here, the academic models, out of 100 sentences, they are failing on almost 94 sentences. This BERT model. The Robota model is failing on around 81% sentences. Right. With this very simple experiment, where you are generating short sentences with neutral nouns and adjectives. What does it say? They don't have a very good vocabulary here. Right. Okay. Let us see some more examples here. Let us talk about this directional case. Right. So in this experiment, we have added positive phrases to a positive sentence. Okay. So for example, this was my original sentence. At the rate Southwest Air great trip on 2672 yesterday. This was my original review, right? I added a positive phrase to it. You are extraordinary. So earlier also it is positive. Now it should be more positive than what it was earlier, right? This is what is my expectation. But how are the models performing, right? So in this case, consider the problems with these two models, the Microsoft model and the Google model, right? They have almost 10% of failure rate, right? So they start treating this as more neutral or negative. Fine. Again, to some extent, at least this is fine, right? So and again, what are the actual scores that these people have reported? So if you see these papers by these different companies and how these models are performing, so if you'll see, it is almost every time almost more than 96% accuracy, almost 96% accuracy. But if you see here, but for these very simple sentences, they are getting this much failure rate. So at least 88% accuracy on these simple instances, right? What is more interesting is here. Maybe not here. Oh, yeah. So there are a few more capabilities. So this checks whether the models have good vocabulary or not. Then there are capabilities like robustness of an NLP model, right? So let us see one example. So for example, if you have a review like this, an original review like this, and if I just append this one, what is this? A mention, right? So mention usually has no sentiment associated with that, right? It's just a neutral one. So in ideal scenarios, the model should not change its prediction. So if it was predicting it as a positive, this original sentence is positive. Now, after appending this mention, it should again predict it as a positive only, right? It should not change its predictions. If you see here, for this Amazon model, in almost 25% cases, it has changed its prediction. Right. Similarly, you can create a lot of such instances, right? Another capability is called NER, named entity recognition, right? Whether the models are able to understand given word is a named entity or not. Right? You understand what is a named entity, right? Whether a given token is a name of a person, organization, place, location, or so on and so forth, right? So for that, what they have done, they switch the location, and that should not change the predictions. For example, my original review was this: a JetBlue, I want you guys to be first to fly to Cuba. This was my original review. What I have done is I have replaced this Cuba with the word Canada. I've just replaced this word Cuba with Canada, right? And what is my expectation? The sentiment should not change, right? Because there is no sentiment associated with the word Cuba. Ideally, there should not be any sentiment associated with word Cuba or Canada, right? And the model should understand that the sentiments cannot be associated with the personality or with the organization or with the country and so on and so forth, right? If it is changing its prediction just based on the change in the name of the entity, then that means it has some problem, right? If you see here, again, this Google model, almost in 21% of the cases, it is changing its predictions. Okay, so this is how you can kind of define a set of capabilities. For each capability, you can define a set of instances, right? Set of sentences. You pass those sentences to the model and see how the model is performing. Okay, let us see some more. There is another very interesting, I'm not talking about this temporal, but this is very interesting. This negation capability. Idea is simple. If you have some negation words like no, don't, isn't, and so on and so forth in your sentence, then the model should be able to understand that this sentence has these negations, right? And if it is not able to understand it, that is a problem. Okay, so let us see. Let us see these two interesting cases. So we created this MFT based instances. Negation of negative at the end should be positive or neutral. So there was this sentence which was negative. I negated this negative sentence, it becomes either negative, neutral, or positive, right? So originally it was like this: I thought the plane would be awful. This is a negative sentence, right? And then I added then I can say, but it wasn't. So overall, what is the sentiment? It is a positive, right? Even though it contains so many negative words, and like the bad words. Okay, what about this? I thought I would dislike that plane, but I didn't. Right. So you have a negative sentence, and at the end again I am negating that negative sentence, right? So this, okay, and our expectation is that it should either predict as a positive or neutral. Okay, and see the failure rates of these popular models. Almost 100% cases, all cases they are failing, right? And these are production level systems which people are buying millions of like on millions of rupees. Okay, very good. Right. So then there are semantic role label based tests and temporal based tests. Okay, so let us just see this one. This is quite simple. Okay, so temporal based capability. Idea is simple. Sentiment change over the time, present should prevail, right? Sentiment can always change over the time, right? In past I don't like this thing, but now I like this thing. So what would be the sentiment? Whether the sentiment should be associated with my past or whether the sentiment should be associated with my present, right? So in ideal scenario, the sentiment should be associated with my present, right? And the model should be able to understand that, right? So for that, what they have done is this: they created some sentences like this: I used to hate this airline, although now I like it. Right. So there is a context of past, and then there's a context, and then the author is talking something about the present. So overall, the sentiment is positive, right? Similarly, in the past, I thought this airline was perfect. Now I think it is a creepy. Now this has a negative sentiment because we have to associate sentiment with the present feeling, right? This is called temporal based capabilities. The model should have model should understand these temporal capabilities, right? And if you see this, all these models, almost 40% errors in these real world good quality models. Okay, very good. They also experimented with this Cora question pair data set, right? I explained this Cora question pair data set. So given a pair of questions that have come from Cora, the model has to predict whether they are same or not, right? So given two questions from Cora, the model has to predict whether the questions are same or not. So by same, I mean similar or not. I won't say same. Okay. For that also, similar set of capabilities. So capabilities like taxonomy, I will tell you what I mean by taxonomy, vocabulary capabilities, robustness capabilities, NER based capabilities, and so on and so forth. Same set of capabilities, similar kind of tests. Similar kind of tests that we have done for sentiment analysis. Okay, let us see. Let us first of all see this vocabulary based capability. Okay, and for that I have created an MFT sentence. Okay, what it says is modifier changes the question intent. So we will we'll start adding some modifiers, right, in my original sentences, and then I will see whether this changes the predictions or not. Okay, so for example, if the two questions are like this, is Mark Wright a photographer? And the another question is Mark Wright an accredited photographer? Are these two same questions? No, they are not, right? Because we have added this modifier, and that changes the entire meaning of the two sentences, right? So model should be able to understand these type of tokens, right? And model will only understand if they have a very good vocabulary. Okay, fine. So let us see some more examples. Let us see this taxonomy based example. So taxonomy means whether model is able to understand synonyms, whether the model is able to understand homonyms, antonyms, and so on and so forth, right? So for that they experimented with this taxonomy based capability, and maybe we can see this one. If you have something like this, just read this sentence, these two sentences. How can I become more optimistic? How can I become more optimistic, right? And the other sentence is, how can I become less pessimistic? Are these two similar sentences? Right? But lot of words are different. The tokens are different between these two sentences, right? And so what is the idea? The idea is the model should have these capabilities. The more this taxonomy based capability, model should understand this taxonomy, that this word is a synonym of the other word, right? This word is an antonym of that word, right? So, and they have experimented with two academic systems this time, Bert and Roberta, right? And you see the failure rates here. That means what? These models don't have a very good understanding of what? Taxonomy. Okay, so that's why, similar to this one. So there's this robustness also. For example, this one. Suppose you have a question like this: can I gain weight from not eating enough? Can I gain weight by not eating enough, right? You can replace can I with, do you think I can gain weight from not eating enough? Are these two questions same? Right? These two questions are same, right? So what it says is, the phrase that you have added, actually doesn't change the meaning of the two sentences, right? But in real scenarios, you can always come up with these kind of questions. So if you have a model, whenever, and that runs at backend in Cora, so whenever you are typing a question, it predicts or it kind of recommends you the similar set of questions, should be able to identify the similar set of questions. And this is what is happening, right? And if you see, just see this, the scores, the failure rates, 69% failure rate, 25% failure rate, and so on and so forth. Okay, so similar to what we have seen for sentiment analysis, you have capabilities for temporal, capabilities for negation, capabilities for co-reference resolution, and so on and so forth. Okay, so for example, this co-reference resolution, yesterday we were talking about it, right? So you have some noun, maybe Mahatma Gandhi has done something, then you will say he has done this, right? Or he was involved in this. So just he is referring to Mahatma Gandhi, right? So do models have this capability? Do models understand that he is referring to this person, right? It is referring to this object, and so on and so forth, right? So for that, what they do is they created some sentences, right? If Joshua and Chloe were alone, do you think he would reject her? This was my first question. The second question is, if Joshua and Chloe were alone, do you think she would reject him? Are these two same or different? Different, right? This is different because he is referring to some other person, she is referring to some other person. Okay, and see the scores, the failure rates. Very poor co-reference resolution capabilities of these models. Okay, that's very good. So this is where I will try to end this session. Okay, but before that, one of the nice thing with this paper was that they have proposed so many capabilities. They have tested on so many models, right? One of the basic thing which is still remains is how we can generate these sentences, the sentences that you are seeing here, right? In order to test our models, we need a good number of sentences for each capability, for each type of MFT or for each type of invariance and so on and so forth, right? So they have created a nice GitHub repo which can help us in generating these sentences. Which can just so what you have to do is you have to define that what kind of sentence you want to generate, and it will generate the sentence. For example, what I want is I want to generate a sentence which has this is, then there is a mask movie. So mask will be replaced by a lot of words, right? You just have to check those words. I want a sentence with this word, I want a sentence with this word, I want a sentence with this word, right? So for example, I'm checking here, I'm saying a good, an amazing, and excellent, right? So the three sentences will be generated by just checking these boxes, right? So again, it is not completely automatic way to generate sentences, but a semi-automatic way to generate so many sentences. So for each capability, for each type of test that you want to do for that capability, you can generate a template sentence, and their system, their repository, their system will generate so many similar sentences that follow this template. Okay, and you can use those generated sentence to test the different models. Okay, so that's all for whatever we have to cover, at least in the basics of NLP and how it is related to the current NLP that people are trying to do. Okay, thank you very much. Any questions? Yes. Yes, yes, yes. So if you see all these models, whether you are talking about this BERT or this Roberta models, and read their papers, you will so they have reported all these the metrics that we are seeing before, right? Precision recall and all these metrics. In terms of those metrics, they perform very well, right? But you look deeper and try to find out this linguistic capabilities, they perform very poor, right? And this is where we should actually kind of come up with, we should do evaluations of any model based on this its linguistic capabilities, right? Because at the end, the model should learn, the model should understand the language it is going to work on, right? So whatever kind of the capabilities we are talking about here, we have talked about here, all these are general purpose linguistic capabilities, right? Each model should have at least these capabilities, right? Whether this is a machine translation model or whether that is a data generation model, translation, summarization model, or so and so forth, right? They should have at least these capabilities. Again, for their domain, for the task that they are trying to solve, you have to define more capabilities, right? That's how you can you can kind of look into their capabilities. Okay. Fine. Okay. Thank you. Bye.